Hello, I'm Rebecca Stinson from Bucknell University's Department of Biomedical Engineering. This summer, I've been working with Dr. Carlo Malaga on a project assessing the stability of thalamic segmentation algorithms for treatment of essential tremor. Essential tremor is a neurological disorder mainly characterized by shaking in the hands. One form of treatment for essential tremor is deep brain stimulation, or DBS. Deep brain stimulation uses electrodes implanted in the brain to stimulate the ventral intermediate nucleus of the thalamus, referred to as the VIM. In order to accurately target the VIM, algorithms based on diffusion tensor MRI data are used to segment the patient's thalamus into its nuclei and subnuclei. Across studies, the number of nuclei used during the segmentation varies due to disagreements on the anatomy and naming conventions for the thalamic nuclei. This study begins to assess the stability of the segmentation algorithm when varying the number of nuclei to determine the optimal number of nuclei to be used when segmenting the thalamus for DBS. Diffusion tensor MRI data from 22 patients undergoing DBS for essential tremor was run through the segmenting algorithm with both 13 and 11 nuclei. For each patient, the algorithm was run for 100 iterations. The volume of each nuclei as well as the centroid location was recorded across each iteration. The coefficient of variance for the volume of each nuclei across iterations was around 62% for both the 13 and 11 nuclei segmentations. This is a high coefficient of variance and indicates that the model does not produce the same size nuclei across iterations. The coordinates of the centroid had a standard deviation between 2 and 3 millimeters for all directions. Both the 13 and 11 nuclei segmentations had similar standard deviations for each coordinate direction. Overall, these results suggest that at 13 and 11 nuclei, the segmentation algorithm is not stable in both volume and position of nuclei. Therefore, a single run would not be able to be used as a predictor of thalamus anatomy. In the future, I plan to continue to assess stability for segmentation using 5, 7, 8, 10, and 12 nuclei, with the idea that smaller numbers of nuclei will produce more stable segmentations. Any stable algorithms will then be assessed using both stimulation and clinical outcome data to determine the accuracy of each algorithm at segmenting the thalamus into its different nuclei.